Hello, everybody. We're here with notebook page 6, the nervous system, a little more in depth than our last one. So, if you need to take down the title card, please do so now. And let's move on. So, let's talk about the nervous system itself here. And the nervous system, is about how the brain communicates with the rest of the body through electrochemical signals through the spine and those other parts of the body. How do we get the messages right from the body to the brain, from the brain to the body, etc.? So this is the central nervous system, CNS for short. We'll use that's what kind of uses the spinal cord and gets those messages to the rest of the body. And most of the sensory information remains on our body's extremities. So, skin, our bones, our muscle, our tissue, right? That's the sensory information that we're getting, touch and feel, and some of those kind of things. The peripheral nervous system, or sensory nerves that relay messages to the brain through the central nervous system. And the other areas do interact to make decisions, to send signals, to kind of make everything work. So there's this whole communication system that's happening that's important when we talk about psychology, and we talk about what could go wrong within the nervous system that could cause issues. So let me put up this slide. Your slide, take it on your own words at this time. Let's move on. So other nervous systems, we're going to discuss neurons kind of in the next slide. And they're a really important part of this unit. It's something that we'll kind of reinforce a little bit later as well. But neurons are nerve cells that communicate through a combination of electrical signals and chemicals. So neurons, each neuron has a different function. And that's something that we'll kind of dig into here of what some of those are. So first we have somatic neurons, which are voluntary muscle movements through motor neurons to move those muscles. So it's what makes you move your fingers, move your toes, etc. Right? So, if you're sitting there and you want to, move your finger up, that's your somatic nervous system, right? And those motor neurons are what's working to tell your finger to move up. Motor neurons are not sensory neurons that relay signals to the brain through sensory receptors, right? So that's more of touch. When you feel something, that information is getting relayed. That's a sensory neuron, but the movement is a motor neuron. So, motor makes you move. Sensory has your senses: touch, taste, smell, sight, etc. The automatic nervous system works on autopilot and ensures kind of the control of key organs to digest food, to make the heart beat, etc. So it does a lot of things that you need to do to keep yourself alive. It's just going to do that automatically. So you don't have to think about breathing if things are going well, right? You don't have to think about, okay, I need to, digest my food. You just need to eat it and swallow it, and it takes over from there, right? You don't need to think about every heartbeat and make it happen, which is probably good. So that's that. Two functions of the automatic nervous system. We have the sympathetic, which arouses or expands energy, like the fight or flight when needed. So, this is, the sympathetic nervous system is basically when you get that adrenaline, for example, we talked about in the endocrine system, that you need to make a decision. This is going to give you that energy to make a decision. I don't know if you've heard stories of like, in the moment someone's lifted a car to free someone in a tense moment. That's kind of the sympathetic nervous system working. I don't know if that's really true, but being able to maybe have a little more strength than you normally have, or run faster than you normally do, right, is the sympathetic nervous system working in a tight situation. Then we have the parasympathetic, which is after the fight or flight. This is what calms you down. So, I use that example, I think, in in the last endocrine system. Someone's someone's chasing, following you at night, and you run home, right? So the sympathetic nervous system is what's going to, expand that energy so you can run fast home and get there. And once you get home, the parasympathetic is going to take over, right? We get that adrenaline slowly kind of drain out, and now we got to slow down your heartbeat. We got to lower your sugar. We got to do all these things to calm you back down. So let me put up the slide here. You can take us down your own words at this time. Let's move on to neurons. So the brain and the nervous system operate with neurons that receive or send electromagnetic signals to communicate. And these neurons are made up of kind of four main parts. And you can see it in the image in the top right. We have the soma, or the cell body. We have the axons, which are covered by the myelin sheaths here. We have the dendrites, which are these right here, and then the synapses, or the axon terminals, right here. So the soma kind of contains the DNA, the stuff that keeps us alive, right? In these neurons, this is what we know that we need and keeps us alive. Electrochemical messages are sent through the axons, which are covered by the myelin sheaths. So it kind of goes through the axons here. We're sending the electrical impulse, and then it travels to the synapses, or these axon terminals in this image. So the synapses are where the neurochemicals are released, and eventually are received by the dendrites, by the other dendrites over here. So, I'm going to show you a crash course video when we finish these notes, either today or the next time, and maybe even an AP Daily video on synapses and the action potential that goes very in depth into it, maybe even more in depth than you need to know. But I think it's important to really visualize what that looks like. Let me put up the slide here. And take us down your own words. Let's move on to neuron communication. And here's that image again. If you want a closer look at it, but I think I covered it hopefully pretty well in the last one, right? Of these, the electrical impulses are traveling in this direction, right, to the axon terminals, and I'll talk about the next piece here in the communication, or what happens next. So once the messages reach the end, they release chemicals called neurotransmitters. And so outside the axon are sodium ions. Here's our sodium ion. And inside are potassium ions and proteins. And this creates a negative charge inside, and this creates a positive charge outside the membrane, right? So we have a negative charge here, positive charge here. Now, to send messages, these charges have to even out. So we have to get a neutral charge for these messages to be sent. So the membrane is going to open up for that to happen. The sodium and potassium pumps, they're called, are activated afterwards to regain balance. So once they open up, these kind of combine, make that neutral charge. And afterwards, the sodium potassium pumps will make sure everything gets back to where it needs to be. And this happens anytime there's a communication, which I think is pretty crazy to think about, right? Every single action that you do, or a chemical that's released, when those signals are sent, this has to happen. And so it's happening just thousands of times a second, every second of your life. So this whole process is known as the action potential, when an electrical signal goes through the axon to communicating neurons, which set the frequency through the signals. So even though the signals are the same every single time, right? So, let me kind of explain that a little bit with action potential. Is if we have a signal that goes through the axon to communicating neurons, it's going to send the same signal every time, right? But sometimes, as we know, when we get a rush of adrenaline, it's not always the same, right? Your rush of adrenaline, it doesn't feel the same in every situation. Sometimes you can get like a little burst of adrenaline. If you wake up and you're scared, you woke up late. Oh, no, I didn't. right? Just a little jolt there versus someone following you home. And you have to run all the way home. So what happens is that signal is the exact same in both those circumstances, but the neurons are what set the frequency and how much do we need, how long does it have to happen. That's going to be a little bit different. So I think that's kind of interesting too, that these electrical pulses are all the same, and the neurons are going to have to set what that is. So let me put up the slide here. You take this in your own words now. All right, let's do reuptake. Before that, I forgot I have the sodium potassium pump image here. If you want to get a good image of this pump, right? All these are together, so it kind of binds the sodium ions and the ATP here, and then splitting that up provides the energy. You can see that this pump is going to put things where they need to be, right? The sodium and the potassium back to where they need to be. So something you can go back and look at if you want a further explanation. But knowing what it is pretty good. So reuptake, neurotransmitters are those chemicals that are released to do different things. So basically, neurotransmitters are the chemicals that are released that make us think or feel certain things. So some examples of these, and this is definitely not a comprehensive list, but some of the ones that we're really going to use in AP psychology a lot. Serotonin, and some of these you may have heard of. Serotonin is kind of social status, happiness, confidence. That kind of gives you that kind of up and feel good kind of high in a way. Dopamine is alertness. Also deals with happiness as well. So that's a lot when we talk about depression. We talk about if you have these kind of symptoms of fatigue. Usually, dopamine can be one of those neurotransmitters that's not getting taken in correctly. Endorphins, which is euphoria, which is pain killing. So that's if you remember from the Phineas Gage video that we watched. That endorphins were, hey, if you take morphine, this will kind of fill that, right? And then norepinephrine is alertness and arousal. So that's kind of being alert. It also deals with sexual arousal, and these are the ones that will kind of deal with the most. These four. So these are sent across the gap to the receptors, the next neuron, fitting into an activator site. So you can kind of see that down here, right? We see the serotonin is kind of getting into the receptor site. See, they're taking in the serotonin right here. And once these have been activated, then you feel the feelings associated. So, hey, we got the serotonin, and that happiness, that confidence goes up. So once they're bound, then the neurotransmitters are sent back to the original ion. A practice called reuptake. So it kind of comes in, receptor site kind of grabs it. Okay, this is the neurotransmitter. So we'll send those feelings and release it back to where it's supposed to be. So everything's where it's supposed to be. Put up the slide here. Take this down in your own words. Fine. All right. So we have agonists and antagonists. And so this is drugs because that is what drugs are, and they deal with these neurotransmitters. So this is kind of how we experience emotions and sensations, right? Is that neurotransmitters taking those chemicals, and we can experience emotion, experience sensation, and many drugs can kind of mimic the euphoria, the alertness. A lot of these things that we're talking about, right? The happiness, the pain killing. That's something that drugs can try to mimic in our brain. So those are our agonists. That's the euphoria, alertness, etc. They're chemicals in drugs that can bind and activate receptors and synapses, thus providing those feelings. So so the drug will go to the receptor and act as something else. So examples of this: cocaine, heroin, nicotine, right? These are drugs that are, have a specific purpose and fit these some of these chemicals that we talked about. So the problem with drugs is that when you take them, right, the reuptake is slowed down. So the receptor site takes in that's what they think is what it thinks is a neurotransmitter, but is this drug, and trying to and so releasing that back. The more that you use it, the longer it takes to kind of release it back, and so that's why we have like overuse can deplete your natural neurotransmitters. Basically, the receptor site. I mean, if you're doing cocaine on a regular basis, right, and you're taking in the receptor site is taking in those neurotransmitters, that's going to fatigue it, and so it's not going to reuptake quick. It's going to kind of release it. It's not going to want to take in those those neurotransmitters anymore, and it kind of starts to kill off the neurotransmitters that you have. It'll deplete that level. So that's why then it becomes, you feel worse afterwards. Every time you feel kind of worse afterwards, use the drugs, and that's where addiction happens. Now you need the drug. It's the only way to get the receptor site working again, because you can't do it naturally. And that's what addiction is, and that's why there are problems with someone tries to have withdrawal symptoms and that kind of thing that's happening. Now, some drugs are antagonists that bind but don't activate the receptors. So they'll bind in. They're not going to activate the receptors. So they're not going to have the same problems as some of the agonists, right? But the issue is sometimes these, can permanently damage you with overuse. So a lot of the antagonists are used to try to treat drug addiction and let people kind of get off of it over time. So something like methadone is used, for someone with a heroin problem. That this is an antagonist drug that will mimic the heroin, but won't have the receptor activation per se. So that you won't get the withdrawal symptoms, but can lessen the addiction. So if you hear like a methadone clinic, that's what that is. This is giving out this drug to kind of replace the other drug in hopes of getting that addiction down. Right, here is the slide if you want to write this down. Your own words. Move on. All right, let's talk about viewing brain activity. So damaged brain tissue are called lesions. And this is kind of the destroying of brain cells. So someone has a lesion on their brain. It's not, a death sentence is not necessarily going to permanently injure them, but it will destroy some brain cells. And could be something that needs to be worked to get back, depending on what it is. The brain can suffer a lot of problems that disrupt functioning. Abnormal amounts of neurochemicals, such as serotonin, lead to depression, reduced neural activity. So, I said that like dopamine, serotonin can lead to depression and other issues. So we need to try to make sure that those neurotransmitters and everything's working correctly as it should be. And so there are ways we can look at brain activity, try to diagnose and treat these issues. And cognitive revolution is something that's used today in live patients, to actually be able to look at the brain and use different methods to examine it. We used to only be able to do it on dead patients. That was, autopsy was the only way to look into the brain. So it had to be dead so we can cut it open and see what was happening. Now we have ways to deal with that, which I'll get into in the next slide. You take this down at this time. All right, let's kind of finish up here with imaging methods. And there's a couple different methods we can use to look at the brain. An EEG or electroencephalogram. I got that one. So this targets the electrical waves down to a specific stimulus, right? It can actually see where that specific stimulus is happening. So when we have an electrical wave communication in our brain, it can see why, it can see where. and it can see if something's not working, what's not working, and we could kind of do it. So that's so that's kind of that one. CT scans. So CT scans are computed tomography is what that stands for. So these are X-rays that reveal the brain damage that have happened. So this can kind of show you if there has been brain damage, where it's happened, show the areas and the extent of it. So the picture up here is an EEG, and then a CT scan will be a little bit more traditional of an X-ray to look at that. PET scans, positron emission tomography, and this shows brain consumption of fuel and glucose. You can see where the brain is working, where the brain is not working, and you can kind of see where things have grown and changed. MRI, magnetic resonance imaging, uses strong magnets to align the spinning electrons in the brain. When the magnet's gone, we can kind of see where they go and get a picture of the soft tissue. So this is one you have to lay down for a portion of time. They use these really strong magnets to kind of get the electrons moving in your brain. And so when they turn the magnets off very quickly, we can see where the electrons kind of go, and we can get a really clear image of the brain and what's happening. And then you have a functional MRI that takes MRI scans less than a second apart, so it does it very quickly, and we can kind of see that flow over time. My brother passed away from brain cancer from melanoma, and he had a lesion on his brain. So he went through almost all of these CT scans, PET scans, MRIs on a consistent basis, sometimes bi-weekly. All of these were put together to see how he was progressing, if there were more lesions on his brain, if cancer had spread, right? It was something they could see based on the MRI and seeing how the brain activity was working in areas where it couldn't work, seeing where the glucose levels were and what was changing, seeing that brain damage specifically with the CT scan. You could see the images of it. So all these can really work together to provide a full image of the brain itself, and there's damage. So something that we have to keep in mind. So I'll put up this slide, and once you're done, that is all for the nervous system, and we'll move on from there.